before we get started, so a couple more people can join us. But hello, welcome back to yet another semester of physiology. Oh, somebody started recording, thank you very much, I forgot about that. Today we're going to be discussing a very chunky topic. Renal physiology is one of the topics that require, at least I think, when I was taught physiology, we had 3 lectures on renal physiology. I'm going to try as much as I can to cram all of that, to condense it all into one lecture. But let's be honest, I have to cut out on some of the details here as well. So basically what I try to do is I try to focus on the topics that are most crucial to understand for the final examination, and on those topics that you probably need for next week's seminar test. So I hope you will all find it very useful. It is 1 minute past. Yes, I think let's get started. So, renal physiology. I have left the contents here, but I'm going to illustrate what I'm going to talk about to you on the examination questions instead. Renal physiology on the final has 11 different examination questions, and they go into a fair amount of detail, actually. What I'm going to be focusing on today are these ones: tubulary processes, reabsorption, secretion, and urine formation, renal blood flow, glomerular filtration, water reabsorption, and examinations of renal function. Those are the ones that involve the most math and physics, and more understanding rather than memorization. So I'm going to try to go through them today. Without further ado, we're going to start with introduction. A lot of the basics of renal physiology you might have already touched on before. You've had anatomy and you've had histology. So what I would consider you've studied during histology, at least, would be like the structure of the glomerulus, the structure of the nephrons. I'm going to go through it, but I'm not going to go into too much detail on it. So the renal functions. The kidney actually has a lot more functions than just excretion of waste and other toxins, but also it controls the body fluid volume through ADH and all the mechanisms associated with fluid regulation. Acid-base balance, it's also a very crucial factor. This is something that you're going to learn in biochemistry during this semester. Basically, there's a fast mechanism and a short mechanism of acid-base regulation. The fast one involves respiration. The short one, the long one involves the kidneys. Blood pressure regulation as well. Then also the kidney metabolizes hormones. It excretes hormones, but it also produces hormones. It is very important for that. And at last, gluconeogenesis. Those, especially acid-base balance and gluconeogenesis, something that I'm going to talk through at length in biochemistry. So I'm not going to go into more detail on that. What is the structure of the kidney? Again, you should be familiar with the most important parts. The functional unit of the kidney is the nephron. There is roughly 800,000 to 1,200,000, 1,200,000 nephrons in the kidney, at least according to Boron. Then it comprises the glomerulus and the tubule. The glomerulus is all the vessels that are contained within the Bowman's capsule. So basically you have like a small capillary network that is lined by epithelial cells where the ultrafiltrate is collected. That is our Bowman's capsule. The most important features that are worth discussing here is the difference between cortical and juxtamedullary nephrons. This is something that you can see on the diagram over here. I'm going to have my handy pen instead. There's something that you can see over here. We have cortical nephrons, whose loop of Henle is more or less limited to the cortex, and we have juxtamedullary, which go all the way to the end of the medulla. This is something that is illustrated on a diagram on the next page, actually a little bit better. Then other important details that you should remember is the vasa recta that is going alongside the loop of Henle in the medulla originates from the glomerulus itself. This has a very important function for the maintenance of the hyperosmolarity that we can find in the medulla, something that we're going to discuss later. And last important feature that I'd like to highlight is that the collecting duct and this is something that you should remember from embryology and histology, the collecting duct loops back towards the glomerulus of its origin, and it meets at the macula densa, which has a very important regulatory function. In case you're not familiar with all the morphological details, I recommend going back to histology and looking at that a little bit more. Next up, here is the slightly better comparison of a cortical nephron and a juxtamedullary nephron. The cortical just touches on the outer zone of the medulla. The juxtamedullary nephron goes all the way inside. What is the difference between a cortical and a juxtamedullary nephron? The cortical nephrons are basically just there for the formation of primary urine. The juxtamedullary nephrons have an important function for the maintenance of the hyperosmolar environment in the medulla. That's the reason why we have less of them. They're not meant to produce any great amount of urine, but rather they are supposed to maintain this environment in the medulla. We're going to discuss how and why later. Then, in order to get the last bits of terminology and basics out of the way, I'd like to discuss differences in blood plasma and filtrate. What does the glomerulus do, or what does the kidney do? It filters blood, but what is the outcome? Blood is normally made from cellular components, proteins, amino acids, glucose, anything that can be found. Plasma is when you centrifuge it, then you will settle all the cellular components at the bottom and you'll be left with serum. Filtrate is what happens in the kidney, which is basically that everything is left, like cellular components and proteins are mostly remain in blood, but we can filter out amino acids and glucose. And what actually ends up in urine is only the ions, and some of them. Everything else is retained in the kidney. Now let's get to the meaty parts. Glomerular filtration. Glomerular filtration is based on the glomerular capillaries. They're a specialized network of high pressure capillaries. Only in the kidney we can find capillaries with such a high pressure level of roughly 60 milligrams of mercury. If you were to have that pressure level anywhere else in the body, you would end up with a significant edema. We have similar capillary networks, for example, in the lungs. But if you were to have this high pressure in the lungs, you would start to have a lung edema. That'd be highly problematic. The filtration apparatus, again, histology, but I'm going to go through it again. The filtration apparatus is based on the endothelium, which is fenestrated, it has small holes, but these holes are only basically there to keep out larger cellular components. Below that, we have the basement membrane, which creates the main part of the filtering mechanism. It is extremely dense and it consists of negatively charged proteoglycans. It creates filtration pores that limit the size of particles that can pass through it to roughly 1 kilodalton. Also, it is very negatively charged due to the presence of proteoglycans, and that also changes the filtering properties quite significantly. And at last, we have the epithelium from the podocytes, which basically are able to regulate the filtration function of the glomerulus somewhat. What determines filterability? Filterability is determined foremost by size of the particle. Anything that is larger than 1 kilodalton will simply not pass through the filtering membrane. But there's also a small differentiation to make between positively and negatively charged particles. Negatively charged particles are repelled by the negatively charged basement membrane. Like charges repel one another, that's why. That means if you have a particle of equal size, but that one is positively charged and one is negatively charged, the one that is positively charged will have a slightly higher chance of passing through the filtration membrane. However, only a minute fraction of proteins is actually filtered out in blood. How does glomerular filtration actually work? Glomerular filtration is the basically when blood passes through the glomerular capillaries, the primary filtrate is formed. The rate at which this filtrate is produced is called the glomerular filtration rate. It is this, and by the way, these are important values to remember. It is 125 milliliters per minute or 180 liters a day. That means every single day, your kidneys produce 180 liters of primary urine. Now, we don't even have that much blood in the body. That means we need to develop a mechanism of retaining these large amounts of water. And this is done by the tubular processes. How is glomerular filtration rate determined? Glomerular filtration rate is determined by two properties: the filtration coefficient, which is Kf, this one right here, and the net filtration pressure. Kf is dependent on the surface area available for filtration and the hydraulic conductivity, which means the hydraulic conductivity is the ability of plasma to actually penetrate through the capillary network in the glomerulus. If we have a large surface area available and our capillaries are well permeable, that means we will have a high rate of filtration going on. Similarly, if we have a high net filtration pressure, our glomerular filtration rate is going to increase. Now, how does net filtration pressure work? I'll try to illustrate it in this diagram over here. Net filtration pressure is the sum of a subset of pressures. The primary determinant of filtration is the glomerular hydrostatic pressure. I mentioned before that in the glomerular capillary network, we have a pressure, an average pressure of 60 milligrams of mercury. That is basically our arterial pressure reduced down to 60 milligrams of mercury and maintained by the afferent and efferent arteriole. It is the primary driving mechanism of filtration pressure. However, it is not the only force. Opposing the glomerular hydrostatic pressure is the Bowman's capsule hydrostatic pressure. You've got to keep in mind that in the same way that the blood is pressuring the inside of the capillaries, all the fluid that is contained outside the capillaries in the Bowman's capsule will affect an equal pressure in the opposite direction. But this pressure, because the pressure in the Bowman's capsule is quite low, is significantly lower. And so far, we will have a net pressure forcing fluid outside of the capillary. Two more pressures have to be reckoned with. If you recall from last semesters and also from biophysics, we have something called osmotic pressure. Osmotic pressure is the pressure that is created by all the particulates and solvents contained within a fluid. And osmotic pressure actually opposes the net filtration pressure. You've got to keep in mind that in the blood vessel, we have red blood cells, white blood cells, proteins, all of that kind of stuff. Their osmotic pressure counteracts the net filtration pressure. At the initial start of the capillary, the concentration of all of these solids is quite low. That means the osmotic pressure opposing filtration is also relatively low. This changes, however, towards the end of the capillary. One last force that is included in the formula is the glomerular colloid osmotic pressure. However, the glomerular colloid osmotic pressure is virtually non-existent as the comparison to what is contained within the capillary, hardly anything is contained outside the capillary. We have basically no proteins in the glomerulus. We have no cellular components in the glomerulus. So we can, for the most part, ignore that force. I already touched upon what happens. Oh, yes. Well, we have a net filtration pressure. If you add all of these numbers up, keep in mind pressure vectors, this is a vector, add up. If you add all of these up, we'll have a net filtration pressure of 10 milligrams of mercury. All of this formula and all of these numbers are absolutely crucial to remember for your final examination. If you do not nail this, this is probably grounds for failure in the final examination. Now, I'd like to illustrate what happens towards the end of the capillary. As blood is filtered, you've got to remember that we are taking fluid out of the capillary, but all the cellular components and all the proteins still left in it. That means the osmotic pressure is going to start to rise, and capillary osmotic pressure opposes our filtration. That means towards the end of the capillary, as we continue, the colloid osmotic pressure is going to increase to roughly 42 milligrams of mercury, and our net filtration pressure will be 0. The pressures will equalize, and when the net filtration pressure is 0, no filtration occurs. This is quite nicely illustrated in this diagram. Well, actually, I was considering removing this diagram, but I wanted to include it for completion's sake. This is a diagram from boron. And the reason why I kept including it is because it actually highlights something that it didn't include on my previous diagram. It includes the afferent and efferent arteriole. and their importance for the maintenance of the glomerular hydrostatic pressure, something that we're going to talk about in the next section. Now, let's discuss what influences glomerular filtration rate. As I said, glomerular filtration rate is dependent on the filtration coefficient and the net filtration force. Any reason why the net filtration coefficient might decrease is usually due to pathological reasons, so renal disease, diabetes mellitus, or hypertension that would damage the vascular walls. Another reason why glomerular filtration rate would decrease is an increase in the pressure in the Bowman's capsule. How could that happen? Imagine you squeeze your ureter for some reason, and urine would not be able to flow down to the bladder. In that case, all the urine that is formed is going to start to accumulate in the ureter, and it's going to pressure back to all the way to the kidney. And this is something that occurs, for example, when you have kidney stones, where the kidneys will not function anymore because the pressure in the Bowman's capsule has increased significantly. Another reason why glomerular filtration rate might decrease is increasing colloid osmotic pressure. And how could that happen? Increased plasma protein concentration, for example, if we are severely dehydrated, or there's, for example, a liver dysfunction. And at last, the main pressure driving filtration is the glomerular hydrostatic pressure, so the arterial pressure, basically. A drop in that pressure will also cause glomerular filtration rate to decrease. And this could be achieved, for example, by sympathetic activity, a decrease in angiotensin II formation, and extreme drops in arterial pressure. The exact details of which we're going to discuss in the next section. Next up is filtration fraction. Filtration fraction describes the relationship between glomerular filtration rate and renal plasma flow. Why is this important? Well, glomerular filtration rate is not just dependent on the, well, yes, it is only dependent on the filtration coefficient and the net driving pressure. However, the filtration coefficient, Kf, can be influenced by the renal plasma flow. And the impact of that is described by the filtration fraction. The filtration fraction describes the amount of filtrate per unit volume of plasma that is filtered through. Renal plasma flow, so plasma flow is all the blood minus the hematocrit, so all the cellular components, divided by the glomerular filtration rate gives us the filtration fraction. The importance of which is quite nicely illustrated here. Imagine we increase, let's look at diagram B, for example. Imagine we have normal glomerular plasma flow. Then the drop in colloid osmotic, the increase in the colloid pressure in the glomerulus is going to be fairly significant, and we're going to have filtration going on throughout the length of the glomerular capillary. However, if plasma flow decreases, in this diagram up here, the plasma that is inside the glomerular capillary is going to have a lot more time to equalize its pressure with the glomerulus. That means a lot more plasma will be actually excreted into the primary filtrate, and the pressures are going to equalize. Towards the end of the capillary, there's not going to be any filtration going on anymore. At the opposite extreme, if we have high glomerular plasma flow, the filtration is going to occur along the entire length of the capillary. That means we're going to excrete a lot more plasma, but the filtration fraction is relatively low as the pressure is maintained throughout. This is basically why, what does this mean? If we increase renal blood flow, the glomerular filtration rate will increase because filtration is possible alongside the entire length of the capillary. If we decrease renal blood flow, pressure is going to equalize, and halfway through the capillary, no filtration is going to happen. Increasing renal blood flow, decreasing filtration fraction. I hope I haven't mentioned this to anyone yet. In case you have any questions, in case I'm talking too fast, in case I'm not making something particularly clear, please feel free to raise your hands, speak up, and I will try to get back to you. We have more or less concluded the topic of glomerular filtration, and we're going to start talking about the regulation of blood flow. So in case anything is unclear with the stuff that I described just now, we're going to take a couple of seconds, minutes, maybe to go through it again. So in case there's any questions, please feel free to raise your hand. If there are no complaints, then I'm going to continue. So, okay. In that case, let's continue. I need to, okay. We discussed how renal plasma flow influences the glomerular filtration rate. Now, let's take a look at how renal plasma flow and blood flow in the kidney itself is actually regulated. There are two main types of regulation, local regulation and systemic regulation. Local regulation is myogenic and tubuloglomeralar feedback. Systemic is neural regulation and humoral regulation. The absolutely most important regulation mechanism that you will find in the kidney is the myogenic autoregulation. You haven't covered vascular physiology yet, but once you do, this is going to be a little bit easier maybe. From histology, you're going to remember that all arteries are lined by vascular smooth muscle cells, VSMCs, as here in the presentation. Now, these VSMCs respond to stretch. That means why would a smooth muscle cell stretch? If we have a sudden increase in renal blood flow, the vessel would start to dilate. And because of mechanosensitive cation channels, the smooth muscle cell would depolarize and start contracting. That way, if the pressure inside the arteriole increases, the smooth muscle cell contracts, it shrinks the arteriole down again, and the blood flow is maintained. This is the absolutely most crucial regulation mechanism in the kidney. And why is that? Because it is remarkably adaptable. It is able to maintain a steady glomerular filtration rate at a ridiculously high range of pressures. Any pressure, any systemic arterial pressure of 75 millimeters mercury to 160 millimeters of mercury will only change glomerular filtration rate by less than 10%. If we go below that, that is basically like if you have a systemic blood pressure of less than 75 milligrams of mercury, you have significant problems. At that case, glomerular filtration or like renal function is the least of your problems. If you have a blood pressure higher than that, that is hypertension, another pathological problem. But the main regulation mechanism of plasma, of renal filtration is the myogenic autoregulation. Another important mechanism is the tubuloglomerular feedback mechanism. Now, if we have one glomerulus, it is sensitive to the filtrate that is detected towards the end of the tubular system. Remember that the ascending loop of Henle loops back to the originating glomerulus. And at the location where the glomerulus and the ascending loop of Henle or the distal tubule meet, we have something called the macula densa. The macula densa, and this is still technically a hypothetical mechanism, however, evidence suggests that this is how it works. The macula densa is lined with cells that are able to absorb sodium chloride. Now, this absorption of sodium chloride is dependent on the amount of sodium chloride in the distal tubule. When renal plasma flow is increased, we're going to have more filtrate, and we're going to have thus more sodium chloride in our primary filtrate. The retention of the sodium chloride is dependent on active transport. That means we're going to have a transport maximum, and if we have a high filtration rate, less sodium is going to be filtered back out of the distal tubule, and we're going to have a fairly high concentration of sodium chloride at the macula densa. At the macula densa, sodium chloride is taken up by the cells in the macula densa, and it is going to cause the depolarization of these cells. What is this going to do? Depolarization of these cells will release paracrine factors towards the afferent arteriole, especially adenosine, and that constricts the afferent arteriole. If we have also, the next thing is it increases the release of renin from juxtaglomerular cells. Renin is the initiating factor for the renin-aldosterone-angiotensin system. This is a cascade that you're going to learn more about in the future, but the basic function is, at the end of this cascade is angiotensin, and angiotensin constricts the afferent arteriole, and that increases the filtration pressure within the glomerulus. So this diagram on the left illustrates it quite nicely. This is the reverse of what I described right now, technically, because Guyton describes it in a slightly different way. But yes, basically, increasing concentration of sodium chloride in the lumen due to increased filtration rate will cause the constriction of afferent and efferent arteriole to reduce glomerular filtration rate and maintain steady filtration. These are the local regulating mechanisms. Now, for the systemic regulating mechanisms, first and foremost, we have the sympathetic stimulus. Now, under normal physiological conditions, the sympathetic stimulus has a fairly insignificant impact. Noradrenaline is released by the sympathetic nerve endings, but is also detected as a humoral factor, and it causes the constriction of afferent and efferent vessels. At low levels of stimulation, the constriction of the efferent vessel is slightly greater, which means if the constriction of the efferent vessel is a bit greater, the pressure in the glomerulus is going to rise, and glomerular filtration is going to rise alongside it. This effect is quite minute. When the sympathetic stimulus is important at high levels, so where will it occur during strenuous exercise or in shock. At that level of high sympathetic stimulus, all vessels will contract substantially, and both renal plasma flow and glomerular filtration will decrease. Furthermore, we have humoral regulation. Again, this is something that you're going to learn about more detail during vascular physiology, but I've included it for completion's sake. Endothelin is a factor that is produced especially by damaged vessels, and it constricts vessels in general, anywhere in the body. In case of the kidney, it constricts afferent and efferent arterioles. Nitric oxide, again, systemic vasodilator. In almost all tissues, nitric oxide causes vasodilation, and it is also produced at basal rates in the kidney. And then at last, prostaglandins, something that we're going to learn about more in biochemistry. They have a minor vasodilatory effect, but their main function is they dampen the effect of noradrenaline and angiotensin II. That means if you have high levels of prostaglandins, something that is especially common during infections or high levels of stress, the effects of noradrenaline and angiotensin II will be lessened. This is something important that you have to account for when giving non-inflammatory, when, for example, giving aspirin, okay, in order to treat inflammation. That may change the glomerular filtration rate and renal function. Again, quick second, we're now done with all the mechanisms that blood flow is regulating the kidney. If those mechanisms are reasonably clear to you, then I'm going to start continuing with tubular processes. Okay, if there's any questions, feel free to raise your hand and I'll try to answer your questions as best I can. If not, then I'm going to continue with tubular processes. So again, the renal, the tubule can be split up into multiple sections: proximal, thin descending, thick ascending, distal, and collecting tubule. And all of them have slightly different functions. I've outlined the functions here, but since we're going to talk about it in more detail during the coming slides, I'm going to go right into that. First of all, we're going to look at the overview of urine production. I said in the glomerulus, anything below the size of 1 kilodalton is freely filtered. However, some substances can also be secreted into urine from the surrounding vasorector or reabsorbed. So substances that are filtered only, for example, would include creatinine. That is a very important factor that you're going to learn about more a few slides down. Filtration and partial reabsorption, so this diagram right here, that is basically for almost any other substance, so especially electrolytes. Filtration and complete reabsorption is for all of the substances that the body cannot afford to lose, especially amino acids and glucose. And filtration and secretion is especially important for the substances that the body needs to get rid of. So an important example is PAH, pyrohypourate acid, and various toxins and organic bases and acids. Overall, how does reabsorption work? We can subdivide reabsorption into active and passive mechanisms. I'm going to start with the active mechanisms. Active mechanisms, well, we have, of course, primary active transport, sodium, potassium, ATPases, proton pumps, and calcium ATPase. The sodium ATPase, the sodium potassium ATPase is the primary driver of almost all active or secondary active reabsorption that occurs in the kidney. So the sodium potassium ATPase creates a concentration gradient for sodium in the tubule. So imagine we have a tubule right here, our tubule cells. The sodium, so this is our tubule here with our primary urine, okay? The sodium potassium ATPase is going to pump sodium out of the surrounding cells continuously and create a very low sodium concentration in here. And that will drive the sodium co-transporter for various other substances. So there's sodium glucose co-transporter, sodium amino acid co-transporter, and various sodium co-transporters for ions, and also a couple of antiporters. Then other active mechanisms include panocytosis. Renal filtration is not perfect, and sometimes we're going to lose a couple of proteins, and these proteins are going to be reabsorbed basically at the proximal part of the proximal convoluted tube. We're going to have small receptors, and they're going to notice when there's a protein attached to it and start to endocytose it. And then last, diffusion. Diffusion, especially in the proximal parts of the renal tubule. Now, we need to look exactly at what happens in which section of the tubule. The proximal convoluted tubule is where most substances that were primarily filtered are reabsorbed as well. And the proximal convoluted tubule, all amino acids, all of glucose, and most of the phosphate is reabsorbed. This is done by sodium glucose or sodium amino acid co-transporters. Furthermore, we have a fairly large flow of water back into the interstitium surrounding the tubule. This creates something called paracellular drag, where all of the solutes in the tubular lumen are also reabsorbed. This includes anything from urea, chlorides, most of the water. All of that is basically absorbed by something called paracellular drag alongside the cell. Because, okay, this is, sorry. We have a very large dependence on the co-transport of sodium. And the more sodium we take out of the tubular lumen, our lumen potential is going to change. If you remember what, basically what happens is, the more positive charge I take out of the tubular lumen and shove it into the interstitium, relatively speaking, my tubular lumen is going to go more negative. So we're going to start forming a lumen negative potential. which is also going to force the diffusion of negative charges across the by paracellular transport. And this is very important for negatively charged ions, especially chloride. And the distal part of the proximal convoluted tubule, a significant fraction of chlorides are reabsorbed due to the lumen negative tubule potential. Then a lot of secretion actually happens in the proximal convoluted tubule as well. Bile salts, oxalates, urate, and catecholamines are actively secreted by antiporters, especially with chloride. The chloride transporter, or the chloride antiporter is fueled by the lumen negative potential. So technically, it is also a form of active transport. Also, pyrethrourate is secreted. Because we are transporting a lot of solvents out of the lumen, water is always going to flow with it. The proximal convoluted tubule is freely permeable to water, and water is going to maintain a steady osmotic gradient across the tubular lumen and the interstitium. So this is one of the other reasons why most of the water is actually reabsorbed in the proximal convoluted tubule. Yeah, so this is talking about numbers. This is what happens in proximal convoluted tubule. Almost all of the amino acids and glucose are reabsorbed along the entire length. Oh, that is something I forgot to mention, bicarbonate as well. Sodium or chlorides are absorbed at equal concentrations as to water, because you've got to keep in mind, we're talking about concentration here, not about absolute quantities. What that means is, as soon as I take one molecule of sodium, a couple of water molecules are going to follow. That means the net concentration is going to stay the same on either side. The only thing that are not only the things that are not reabsorbed actively or secreted actively are going to increase in concentration relatively in the proximal convoluted tubule. I forgot to talk about bicarbonate, but this is actually very important, and we're going to look at this in more detail on this slide. Bicarbonate is very important for the maintenance of the acid-base balance in the human body, and we cannot afford to lose bicarbonate. However, reabsorbing bicarbonate is not quite easy. The reabsorption of bicarbonate occurs by the active secretion of protons into the tubular lumen. This, in the proximal tubule, occurs by a sodium proton antiport. Now, these sodium ions are going to link up with our bicarbonate ions and form bicarbonic acid. And through an enzyme called carbonic anhydrase, we're going to start forming water and carbon dioxide. And carbon dioxide as a gas is able to freely diffuse back into the epithelial cells of the tubular lumen. And then within the tubular lumen, through the same enzyme, carbonic anhydrase, we're going to start forming bicarbonate again. The proton that is formed in the process will be transported back out into the tubular lumen, and the bicarbonate through a sodium bicarbonate symport will be moved back into the interstitium. And this is the mechanism how most of the bicarbonate is reabsorbed in the tubular lumen. Bicarbonate reabsorption without the secretion of protons does not work. The secretion of protons is absolutely crucial for it to function. Let's look at the numbers a little bit. Most of these numbers are not crucially important, but what is absolutely crucial to remember is that all of the proteins and all of the amino acids and glucose are fully reabsorbed in the proximal convoluted tubule. The only scenario where that would not be the case is when the concentration of glucose in plasma would be too high. When is that the case? Diabetics. Since the reabsorption of all of these substances is active transport inherently is limited. There is a maximum number of transporters available. And if the concentration of glucose in the lumen is too high, then we're not going to be able to reabsorb all the glucose that was secreted into the lumen of the tubule, and some of it is going to remain in the filtrate. And this is what happens in diabetics that are not treated. They're going to start having diabetes insipidus, which is the frequent urination due to the fact that because a lot of glucose remained in the primary filtrate, the osmolarity of the primary filtrate is also higher. and not as much water can be reabsorbed. This is very crucial to remember. I don't remember the exact concentration at which the sodium glucose transporters are maxed at, but that is actually something that, if I think of it, you should possibly look up in the textbook and remember for the exam. Now, what about the other substances? Phosphates are reabsorbed at 80 to 90%. Bicarbonates, 85% are reabsorbed. Sodium and chlorides are absorbed at 67%, similar to water. Keep in mind that water always moves with sodium at roughly equal concentrations. And because, as we said, there's no boundary for the water to cross the proximal tubular membrane, the differences in osmolarity caused by the transport of solvents back into the interstitium are going to be equalized immediately by water, and the concentrations or the absolute quantities reabsorbed are going to remain roughly the same. And last but not least, 50% of urea is reabsorbed. Of these numbers, what you absolutely have to remember is proteins, maybe bicarbonate, and sodium and water. The rest, not quite as important. Now, let's continue. The thin descending loop of Henle. What is the function of the thin descending loop of Henle? It is the concentration of the filtrate. How is it doing that? It is removing water by the free diffusion across the membrane of the descending loop. Virtually no transport of solutes goes on in the descending loop of Henle, which causes our small increase, as you can see in the diagram here, small increase in concentrations of practically every single solute in the thin descending loop. For the thick ascending loop, so the second half of this diagram, the opposite is true. The thick descending loop is impermeable to water, but a lot of solvents are actually reabsorbed. Sodium chloride, potassium, and protons are reabsorbed by secondary active transport. So there is a very important transporter that you have to remember. That is the sodium chloride and potassium co-transporter and the sodium proton antiporter. All of this is fueled again by the sodium potassium ATPase. As you might notice, we're actually pumping potassium into the cell. How does this affect the sodium chloride potassium symport? Potassium is the only thing that is basically not particularly reabsorbed in the thick ascending loop of Henle, and it is able to diffuse out of the tubular cell on either side. So the net effect of this reabsorption is relatively small, but it is important for the retention of sodium and chloride ions. Furthermore, because we are again removing a lot of negative charges this time around, because of the reabsorption of chlorides, we're actually going to start creating a lumen positive potential. And this is then going to drive the reabsorption by diffusion of all the positively charged ions, so sodium, potassium, magnesium, and calcium. This mostly occurs by parallel cellular diffusion. The term lumen positive and lumen negative potentials, I think, are a must for the oral exam, and you should also remember where exactly and when exactly they occur. The lumen positive potential, as I said, drives the reabsorption by diffusion of all of these ions in the thick ascending loop. Now, because this section of the loop is water impermeable, technically we are going to dilute our urine. We're not going to dilute it by adding more water, but we're going to dilute it by removing all of the contents. Last, angiotensin II increases sodium retention. It does that by, if I remember correctly, increasing the activity of the sodium potassium ATPase, but that's something I'm going to get to later. Now, the distal convoluted tubule. The distal convoluted tubule and the collecting duct, for our intents and purposes, should be separated a little bit. In the proximal part, or in the early part of the distal convoluted tubule, the primary function is the dilution of urine by removal of solutes and fine-tuning. The distal convoluted tubule is impermeable to both water and urea. Both, again, features absolutely crucial to remember. And what is happening in the distal convoluted tubule? We are going to have, again, our sodium-potassium ATPase creating a sodium outflux out of the tubular cell. The sodium-calcium antiport is going to drive calcium out of the cell, and sodium will diffuse back into the cell as a result. That means we have a very low calcium concentration in here, which is going to allow our calcium channel here to reabsorb significant quantities of calcium from the tubular lumen. Similarly, we're going to reabsorb significant quantities of chlorides due to the presence of the sodium chloride cotransporter. The sodium chloride cotransporter is induced by aldosterone. And furthermore, we're going to have a chloride potassium symport at the basolateral end of the cell. The distal, the late convoluted tubule and the cortical collecting duct, their function is a little bit more elaborate. Their function is, again, the fine-tuning, water retention, and also, in addition, the acid-base balance in the body. We have water permeability, but it is still urea impermeable. We have three types of cells in the collecting duct. The principal cells account for 2/3 of all the cells in the collecting duct. And their function is the sodium reabsorption and potassium excretion. It is induced by aldosterone. Aldosterone increases the function of the sodium-potassium ATPase. And when it does that, it'll start removing, or it'll start exporting potassium into the tubular lumen whilst retaining sodium. The next two types of cells are the intercalated cells. We have two types of intercalated cells, type A or alpha. I'd like to remember this: type A against acidosis, type B secrete bicarbonate. Type A are responsible for the maintenance of the acid-base balance. Type A intercalated cells have sodium-potassium ATPases and proton pumps that continuously move, sorry, not sodium-potassium ATPase. They have proton-potassium ATPases and proton ATPases in the apical side of the membrane, which continuously pump protons into the tubular lumen. And if you remember from the previous slide, in the proximal convoluted tubule, this enables the formation of carbonic acid, the formation of, well, the breakdown of carbonic acid into carbon dioxide and water, and the reuptake of that carbon dioxide into the tubular cells and the formation of bicarbonate. So by type A intercalated cells prevent the loss of bicarbonate ions. Type B do the exact opposite function. And type B exchange chloride ions for bicarbonate ions. And thus basically counteract alkalosis. This is a topic that you're going to understand possibly a little bit better once you start discussing this chapter in biochemistry. Then it's going to start making a lot more sense. But for the purposes of the physiology test next week, what I'm telling you right now should be absolutely sufficient. And last but not least, ADH. ADH induces aquaporin 2. The number 2 is quite important. And the apical part of the principal cells, and that increases the permeability to water. Without ADH, antidiuretic hormone, the collecting duct is virtually impermeable to water. And ADH is one of the primary determinants of the water retention within the kidney. The last section of the tubule that we're going to discuss is the medullary collecting duct. That is the very last section of, and in the already very hyperosmolar section of the medulla. The medullary collecting duct is primarily important for the determination of how concentrated our urine needs to be. If we are significantly dehydrated, our brain is going to start releasing ridiculously high quantities of antidiuretic hormone, And that is going to start presenting aquaporins 2 on the apical side of the membrane, and water is going to be able to freely diffuse back into the interstitium. But also, furthermore, the medullary collecting duct is permeable to urea, which also increases the diffusion of water back into the interstitium, the exact mechanism of which we're going to discuss in a minute. That is it for the tubular processes. I'm going to again ask you, do you have any questions? And I'm going to take a sip of water in the meantime, actually. We are not quite, well, we are slightly over halfway through our presentation. And considering we're going at we're going at a faster pace than I expected. So I am just going to continue. Now, okay. Let's discuss water management. Tubular water management looks like follows. I said that the proximal convoluted tubule is permeable to water thanks to the export of especially sodium chloride in the proximal convoluted tubule, and water is simply going to follow by paracellular transport and aquaporin 1. In the descending loop of Henle, the descending loop of Henle is water permeable. And because as the loop of Henle descends into, I'd like to have my pen back, that is. As the loop of Henle descends into the medulla, the osmolarity surrounding it is going to increase. Because it's freely permeable, the osmolarity in both interstitium and inside the tubule is going to equalize. Keep in mind, osmosis from an area of high water concentration to an area of low water concentration. So the concentrations of the concentrations are going to equalize, and the tubule fluid is going to become hyperosmolar. At the ascending loop of Henle, the reverse is true. It is water impermeable. Solids are going to be exported, and that will decrease the osmolarity of the tubular fluid. There are there's no ADH-dependent transporters in the ascending loop of Henle, so water reabsorption does not occur. And then, at last, the collecting duct, water permeability is regulated by ADH. Now, this is what it looks like when ADH is not secreted, then the osmolarity is going to be fairly low. We are going to discuss exactly how the water retention mechanism works and how the concentration of urine works now. For the concentration, before that, this is what it looks like if ADH is secreted at maximum volume. The osmolarity, instead of 50 osmoles, 50 milliosmoles, is going to be around roughly 1,200 milliosmoles. The exact mechanism of which we're going to discuss soon. Now, in order for water reabsorption to occur, we need to have a hyperosmolar interstitium in the medulla. But that doesn't come by itself. We need to somehow create it. And all the transporters that we have available to us, all the sodium potassium pumps, all the antiporters, they by themselves are not able to establish a concentration gradient necessary for this hyperosmolar environment to form. Ion pumps themselves can create a maximal concentration gradient of 200 milliosmoles. And that by itself will not create the hyperosmolar environment that we need for the water retention to occur. For this, the body has developed something rather ingenious, which is something called the countercurrent system. The exact mechanism of the countercurrent system, again, is something that is absolutely crucial for the exam. And I hope I can do a good job of explaining it to you today, so you're going to be able to explain it in the examination as well. The countercurrent system works something like this. let's presume that in our descending, this is our loop of Henle right here. And let's presume that in this loop of Henle, we're going to have equal concentrations of everything in the loop itself and in the surrounding interstitium. Now, at start, when we start activating our small pumps in the thick ascending loop, remember that they're going to transport sodium ions out of the tubular lumen into the interstitium. And they're going to establish a concentration gradient of roughly 200 milliosmoles from the tubular lumen towards the interstitium. Now, what is going to happen on the other side? Keep in mind, this region on the descending loop is completely water permeable. That means concentrations are going to equalize, and similarly, the fluid on the inside the descending loop is going to become slightly more concentrated. How is the osmolarity of the interstitium maintained? Despite the fact that actually water is now leaking into the interstitium? Well, this is because the sodium, the pumps work continuously and continuously transport ions out of the tubular lumen and the ascending loop, and also because the blood supply of the countercurrent system is a very elaborate system that enables the maintenance of this concentration gradient. We're going to get to that in a second. Now, let's continue discussing how the countercurrent system is formed and how we get to our hyperosmolar environment in the medulla. When the descending limb has reached equilibrium, let's presume that tubular fluid starts moving slightly downstream again. That means our slightly more concentrated fluid now moved to the ascending loop. Here again, we're going to have equal concentrations of slightly more concentrated tubular fluid. And that also means that our pumps are going to be able to start working again, because it doesn't matter whether they're going to start working from a concentration of 400 milliosmoles, 200 milliosmoles, or 1000 milliosmoles. The only thing that matters is the concentration gradient between interstitium and tubular lumen. That means in the region where the concentration has been raised a little bit, is now equal to the interstitium, the pumps are going to start creating a concentration gradient of 200 milliosmoles again, raising the concentration of the interstitium to roughly 500. Now, this is only true for the regions that have already been in contact with a slightly more concentrated urine. Now we can repeat this cycle over and over again. Fluid will start moving into the interstitium, and the concentrations between tubular fluid and interstitium are going to equalize. That means our urine on this side is going to be more concentrated again. This concentrated urine is going to start, moving again to the other side again, where then we can increase our concentration gradient. And this is basically the cycle, and this is what it looks like as a whole. Movement of fluid, equal pumping, equalization of concentrations, and continue. And after repeating this a couple of times, the absolute bottommost tip of the loop of Henle is going to establish a concentration gradient of 1,200 milliosmoles towards the top end of the loop of Henle. And this is why the interstitium has such a hyperosmolar environment. Now, why is this important? In order for us to reabsorb water in the collecting duct, the only way we can reabsorb water is if we then open up our aquaporins, and the concentrations of water are going to equalize again. That means water is going to start rushing into the interstitium. This is what the left side of the picture is. Water is going to start rushing into the interstitium, and the concentration and the urine is going to become more concentrated, concentrations equal to the interstitium. This is what enables us to concentrate urines to something far greater than our standard run-of-the-mill sodium-potassium exchanges would be capable of. Now, I haven't yet discussed the role of urea in this, but it is again something highly important for the examination, so here it is. Urea is freely filtered in the glomerulus and reabsorbed partially in the proximal convoluted tubule. All of this region is reasonably permeable to urea, but concentrations are going to remain relatively stable. However, as urine is since urine moves down the collecting tubule, and water is going to start, if water is going to be retained due to the large release of ADH, then our urea in the collecting tubule is going to start increasing concentration, creating a concentration gradient of urea towards the interstitium. And if ADH is secreted, also specific urea channels are actually going to be presented towards the membrane as well, and urea is going to be able to diffuse back into the interstitium. This further increases the osmolarity of the interstitium, and again, further increases the amount of water that we're able to reabsorb from the tubular lumen in the collecting duct. Now, this urea is going to move into the interstitium and basically at volition move back into the collecting tubule in the medulla. And this basically creates a cycle of urea that constantly moves between the collecting tubule and the loop of Henle, raising the osmolarity of the interstitium if aquaporins are opened. Now, I said, well, first of all, how is this concentration maintained? We also need a blood supply in the medullary region of the kidney. Remember at the start that I mentioned the vasa recta originates from the glomerulus and loops all the way back to the origin, the glomerulus of origin. This creates a similar countercurrent system in the vasa recta, where the concentrations of solids and water are going to equalize with the interstitium. As the interstitial osmolarity rises, water is going to start moving out of the interstitium, but as the blood moves back in towards the cortex, water is going to be reabsorbed and transported back towards the renal vein. This countercurrent system of the vasa recta is crucial for the maintenance of the hyperosmolar environment in the medullary interstitium. Now, again, we've covered a fairly complex and chunky topic, and I'm gonna again ask you any questions. Please raise your hand. Eric asked whether the countercurrent system is the same in the cortical and the juxtaglomerular nephrons. The countercurrent system is no, it is not. The countercurrent system is the system that is present, and I'm going to go back to the slides, illustrating the difference between the nephrons. Wait a second. Okay. Cortical nephrons do not loop as far into the into the medulla. Yes, the only reason why they do not loop as far into the medulla, and the countercurrent system is basically negligent. The reason for the countercurrent system is we need to have a hyperosmolar medulla. And important for the maintenance of this hyperosmolar environment are the juxtaglomerular nephrons, which create this, which basically have this very long loop going all the way down to the renal calyx, basically. Does that sort of make sense? Okay. If there are no further questions, I'm going to continue with I'm going to continue with the functional assessment of the kidney. Examination of renal function. This is the last section of our presentation, and yeah, I hope it wasn't too dense so far. We already discussed the glomerular filtration rate. Now, basically, the glomerular filtration rate and clearance is equal to one another if the substance that is filtered is neither secreted nor reabsorbed. Clearance, this is basically a useful way of quantifying the excretory function of a particular substance. Why is this important? If a clearance is greater than the glomerular filtration rate, that means we can say, okay, the substance is actually actively secreted into the tubular lumen. If the clearance is less than the glomerular filtration rate, the substance is reabsorbed. What is crucial to remember for the examination is that clearance is the definition of renal clearance. The volume, the definition is the volume of plasma that is completely cleared of a substance per unit time. This is not technically true, like we cannot say, yes, this particular volume. It is more of a mathematical function, but it is still, it is the definition and you have to be able to explain it during the examination. The way it is calculated is as follows. We can examine the clearance by measuring the concentration of a substance called inulin in both plasma and urine, and the flow rate of urine. Inulin is a non-endogenous substance. We have to actively inject it into the human. However, when we measure the concentration and measure the rate at which it is filtered from plasma, we can plug it into this formula right here, and it will return us the glomerular filtration rate. And also its clearance technically. But if, again, and this is something that we're going to get to in this slide, if a substance is freely filtered and not reabsorbed or secreted by the renal tubulins, its clearance is equal to the glomerular filtration rate. Inulin is considered the gold standard for this. However, nowadays, what is mostly done is creatinine, as it is, we don't have to inject something into the previous before the examination. The creatinine is a product of the breakdown of muscles and is produced continuously. And creatinine levels throughout the day or throughout the human life are reasonably stable unless there are some metabolic problems occurring currently. Then the last section that we should mention is renal plasma flow. Renal plasma flow, I mentioned this in the previous slide, is basically the amount of plasma that is going through the kidneys at any given moment. How are we able to calculate it? If we have an imaginary substance that, if it enters the kidney, is 100% excreted, we can use that to calculate the total plasma flow from that. If we say that, for example, 100 milliliters of plasma enter the kidney every single second, and 1 milligram of plasma, 1 milligram of the substance is PAH. If that substance is 100% cleared and there's no PAH left at the end of the renal tubule, we should be able to find all of it in the collecting urine. And if we multiply the urine production rate and the filtration of urine, we can figure out the amount of plasma that had to be filtered in order for this concentration of PAH to be present. PAH is not perfect. It actually is not 100% excreted in the kidney, but it is almost perfect. It is excreted by roughly 90%, and that is physiological across the board. And if we want to have accurate values, we can account for that in our calculations. And that, I think, is it, actually. I am surprised that we finished sooner than I anticipated. I expected this to take longer. But that means that we have significantly more time for questions. So in case you have any, now is the time. If you have any questions about other topics that I haven't covered in this lecture, also please feel free to ask, or if you want me to go through something in slightly more detail, now's the time. You can also open up your microphone if you want to. Somebody...
Excuse me.
Yeah.
Is it possible to have a short review over the juxtaglomerular apparatus?
Yes, of course. Yeah.
Great, thank you.
Any other questions? Okay, if there are no more questions, then I'm going to end this recording for now, because in order to make a better illustration of how it looks, the glomerular apparatus, I'm going to require more images, which I can't actually reference in my presentation right now. And because I'd like to keep all my sources included, I will do that separately from this. Before you leave me, and before we start discussing a couple of questions, I'd like you to take a time. There's a QR code in the presentation. If you're able to scan it and answer a quick survey, or you'll be able to find the survey also in the comments to this lecture, to give us a little bit of feedback towards the presentation, towards the lecture, towards me, I would greatly appreciate that. And with that, I'm going to end the recording and start discussing, the juxtaglomerular apparatus.